What I want to talk about in this module is price and income elasticities of demand. Up to this time, in the theory of the consumer, we put preferences together with constraints to derive the individual's demand curve. Here we'll derive the market demand curve, and then we'll do some things with it, and that's where we'll be illustrating the price and income elasticities. So let's get on with it. So first of all, what is market demand? What we've been deriving up to now is individual demand. What market demand is technically the horizontal sum of individual demand. But let me show you what I mean by that. So suppose we have two individuals in our market. And that's the whole market, just those two individuals. Conceptual thought is, choose a price, and at that price, here's the quantity that individual 1 wants, x1. At that same price, this individual 2 has a different demand curve, and he or she wants x2 units. If they're the only individuals in the market, and then at that same price, the market demand quantity at that point is x1 plus x2. So we're just literally summing up this amount here with this amount here at that price to get this bigger amount here. And the idea is that any point along the market demand curve is the horizontal sum of the quantities that individuals want at that price. So to sum up, fix the price, add the quantities. And it's a horizontal summation. At each price, we're asking how much does each person want to buy, and add those amounts up to get the market. So how do we use that, sort of like in problem-solving context? And so here's an example. Let's suppose that we have two individual demand curves, one for individual 1 and one for individual 2. And now's a good point to note that we generally work with linear functions in this class, even though the theory doesn't necessarily imply linear functions. As we saw previously, the individual demand curve from the u equals xy was not linear, but we work with linear functions because they're reasonable approximations and they're much, much easier to work with. So that's just an aside. That's why we've jumped over to these different kinds of functions, but they're the easy ones we like to work with. Anyways, back to the story. So for individual 1, we have a demand curve P equals 100 minus 2 times Q1. For individual 2, we have a demand curve P equals 400 minus 4 times Q. Now we've subscripted the Q's because there are these different individuals. Now here's the trick. For horizontal summation means summing quantities. So the trick is we needed to rewrite these two demand curves here as Q equals. And so we solve the first one and get Q1 equals 50 minus a half P. Now how did I do that? Just a quick refresher. If I have P equals 100 minus 2Q1, I could divide everything by 2 to get Q1 without anything multiplying it. I'd have 1/2 times P equals 50. That's 100 over 2 minus Q1. And then I could get this as a function of Q1 by adding Q1 to both sides and subtracting a half P from both sides. And that's what yields this right here. Similarly, I can get an expression for Q2. Well, now I'm ready to horizontally sum, now that I have these demand curves expressed as Q1 equals and Q2 equals, because the overall market demand is the sum of Q1 and Q2, and it equals, we'll just call it big Q here. So it equals 50 plus 100, or 150. And over here, then we add up the coefficients on the prices. We have minus a half, minus a quarter, and so we have minus 3/4. And here's an expression, or really an equation, for the market demand curve. Now we're kind of done, but we're kind of not done, because we often like to express these demand curves as P equals. So let me just show you. What we left off with at the last slide was Q equals 150 minus 3/4 P. If we want to get this as P equals, we can multiply everything by 4/3. That gives us 4/3 times Q equals 4/3 times 150 minus just P, because 4/3 times 3/4 is just 1. Re-expressing it in terms of P, we get P equals 200 minus 4/3 Q. Now one little kind of geeky note to make here is that this is really only true for prices less than or equal to 100 when both consumers are in the market. If I just flip back quickly, if you look at these demand curves, P equals 100 minus something and P equals 400 minus something. Well, at prices above 100, individual 1 is not in the market. So only at prices below 100 are both individuals actually in the market. Okay, in any event, there's the market demand curve. And so the point of these few slides was just to make it clear to you how it is you go about doing horizontal summation of demand curves. This is something we do at a few different points in this course, so it's worth spending some time on. All right, though, let's talk about working with market demand. So what is it that market demand does? The market demand curve relates the price of a product to the quantity demanded, holding other things constant. Well, what does that mean? Well, for example, it holds income constant. Remember, because if income changes, we'd be shifting the demand curve. But along the curve itself, we're just considering what happens when we change prices, and in particular, what happens to the quantity demanded in the whole market. Now, we generally write this, as I mentioned, in terms of P. P equals some A minus B times Q, something like P equals 100 minus Q or whatever. We'll see lots of different examples. And the market demand curve is a super useful tool. It allows us to answer all kinds of questions. What happens to the quantity demanded if the price were different? Then we can use it also to think about what would happen to revenue, many different things. One thing we'd like to have, though, is a measure of the responsiveness of the quantity demanded to prices. And we have this concept called the elasticity of demand, the price elasticity of demand. And we say it's unit free because, suppose we were denominating prices in pennies. Well, if we were denominating them in pennies versus dollars, we'd get responses that are 100 times different, even though really that's not meaningful. What's meaningful is the percent change in the quantity or the percent change in price. And so, in fact, that's how the elasticity is defined. We call the elasticity this epsilon, and to be a little bit formal about it, we call it epsilon Q comma P. It's the quantity response to a change in price. And so this delta Q over Q is the change in Q over Q divided by the change in P over P. And so what is that? Well, that's really the percent change in quantity divided by the percent change in price. Now you can just rewrite this as delta Q over delta P times P over Q. So this is a pretty handy definition of the elasticity. If you're a calculus person, you can also think about it as the derivative of Q with respect to P, or the slope of the demand function, times P over Q. But this is the definition we'll typically work with right here. Now, a few definitions. First of all, the elasticity is a measure of the responsiveness of quantity demanded to price, and so we already know the demand curve slopes downward, so the elasticity is going to be negative. But let's talk about this. So when the elasticity is less than -1, and when I say less than -1, I mean a number like -2 or something, we call it elastic. When the elasticity is -1 exactly, we'll call it unit elastic. When the elasticity is greater than -1, but still negative, so a number like, let's say, -0.5, we'll call it inelastic. Let's work through an example with a particular demand curve just to make sure we've got this straight. So here's this straight line demand curve, Q equals 10 minus P. The elasticity, and let's jump to this version of the formula that we said is pretty handy. So it's the change in Q with a change in P, times P over Q. Now what's the change in Q with a change in P? We'll look back over at this demand curve. If P went up by 1, what would happen to Q? Well, Q would go down by 1. So delta Q delta P is just -1. And of course, that's also the slope of this demand curve. And if you're a calculus buff, it's the derivative. What's the elasticity, though? It's not just the slope. The elasticity is the slope, -1, times P over Q. We can take that one step farther down here. we can say it's P over an expression for Q that involves P, so Q equals 10 minus P. And so now we've got the answer, although even still it's not quite the answer in the sense that it's not a number yet. One thing you can see is that along this demand curve, the elasticity is going to be different. Let's take a look over at this picture for a second. Here's a picture with price on this axis and quantity on this axis. And the demand curve has an intercept of 10 on the price axis and an intercept of 10 on the quantity axis. Let's look along that demand curve and calculate the elasticity. So for example, how about P equals 8? Well, at P equals 8, this elasticity equals minus 1 times 8 over 10 minus 8, 10 minus 8, or 2, so it equals minus 4. It's elastic. What about at P equals 4? Well, at P equals 4, this elasticity equals minus 1 times 4 over 10 minus 4, or 6, so it equals minus 2/3, and at that point it's inelastic. So one of the punchlines from this slide ought to be that the elasticity varies along a linear demand curve. There is a point where the elasticity is literally minus 1, and then for this demand curve you see it's right here at 5 and 5. We'll talk more about that in a minute. One thing that elasticity is related to is maximum revenue. So let's stick with the demand curve that we've been working with, and let's consider various price quantity combinations along that demand curve, and let's calculate the revenue at each point as well as the elasticity at each point. And we'll see something interesting happens. So when the price is 9, the quantity along the demand curve is 1, so revenue is 9 times 1, or 9. If we were to calculate the elasticity at that point, we'd find it's very elastic. It's minus 9. When the price is 8, quantity is 2, revenue is 16, and the elasticity is minus 4. When the price is 7 and the quantity is 3, the revenue is 21, and the elasticity is minus 2 1/3. When the price is 6, quantity is 4, revenue is 24. Notice that so far revenue has been rising, 9, 16, 21, 24. When we get to 5 and 5, revenue actually reaches the highest we've seen it. It's 25, and the elasticity equals minus 1. Let's keep going. When the price is 4 and the quantity is 6, the elasticity is minus 2/3 and the revenue is 24. Well, revenue is falling now. There is indeed something special about what's bold in this table. This is the point where the elasticity equals minus 1, and it's the point where revenue is maximized. So what's in green here is the punchline, that revenue is maximized when the elasticity equals minus 1. And when I say when, I mean at the price-quantity combination along the demand curve such that the elasticity equals minus 1. Let's switch gears and talk a little bit about intuition instead of models. Let's think about what is it that determines the price elasticity of demand. You know, the price elasticity of demand is how responsive the quantity demanded is to prices. Probably the best answer here is the question of the availability of substitutes. If there are no substitutes for a product, it's difficult for consumers to substitute away from the product if the price goes up. And so, think about in this second bullet point here, asparagus versus vegetables versus food. Starting with food, well, there really is no substitute for food. If you don't have any food, you will die. And so the demand for food is inelastic. Even if price went up a lot, you still have to buy food or else you die. Now think about vegetables. Vegetables are very good and healthy and so forth. If you can't get vegetables, though, you could have fruit or grain or something else. You might eventually develop scurvy or something, I don't know. But still, there are some substitutes for vegetables, whereas there are no substitutes for food. And so the demand for vegetables would be less inelastic. It would be more responsive to price changes than would the demand for food generally. Now think about asparagus, which is a particular kind of a vegetable. Are there substitutes for asparagus? Yes, there are a lot of things you could have instead of asparagus. They're not identical to asparagus, but they are substitutes. And so if the price of asparagus were to change a lot, people would shift away quite a bit. And so we think of the demand for asparagus as being elastic compared to the demand for vegetables or certainly food. So another way to think about it is just to think about like particular brands versus categories. And in general, categories of products have more inelastic demand than particular brands. Because again, one of many brands is just one thing with lots of substitutes, whereas a category may have fewer substitutes. One final point I want to make is that in addition to the availability of substitutes, there's also the question about whether consumers are informed about the availability of substitutes. So think about if you know the prices of some product everywhere, and then you see the product somewhere and a little higher than you thought it, and then you know it to be elsewhere, well, you'll have a big quantity response. You won't buy it from the vendor who's charging a lot if you know about its cheaper price somewhere else. Whereas if you don't know, if you really don't have good information about the availability of substitutes, you may not be very responsive. So better informed means more elastic probably. And that's kind of interesting to talk about in this 21st century, because nowadays people have lots of information about prices of products, prices of alternative products elsewhere. And so that tends to make people more elastic in their demand. All right, some takeaways on this first part. First of all, the market demand is the horizontal sum of individual demand curves. Second, the price elasticity of demand, which is a unit-free measure of responsiveness, we call it epsilon, and it's calculated as delta Q over delta P times P over Q. What are some ranges that matter for us? Well, we call it elastic if the elasticity is less than -1, a number like -2. We call it unit elastic if the elasticity equals -1. And we call it inelastic if it's bigger than -1, meaning a number like -0.5. Revenue is maximized at the quantity-price combination such that the elasticity equals -1. And finally, an intuitive point, narrower categories of products tend to be demanded more elastically because they tend to have more substitutes. Now I want to talk about the income elasticity of demand, and this gives rise to a way of breaking down goods, or a taxonomy of goods. First, a definition. So the income elasticity of demand is, well, it's analogous to the price elasticity, but it's the change in Q over change in income times income over Q. And conceptually, it's the percent change in the consumption of a good with a 1% increase in income. And it's useful for classifying goods in ways that you'll see in a minute. So first of all, what's going on when we change income? Well, we can go back to our commodity space diagrams. We have some good on this axis, fish, some good on this axis, steak. And what the blue lines are budget constraints that are shifted parallel. In other words, all that's going on between them is different levels of income. And so now what we're asking is, what happens, for example, to the quantity of fish chosen as income goes from the income on the lowest budget constraint to the income associated with the second budget constraint? And what we see is that the demand, or the quantity consumed, goes from F1 to F. As income rises from the lowest budget constraint to the second one, the quantity of steak chosen increases from S1 to S2. So what is that illustrating? Well, as income rises, the quantities of F and S consumed both rise. So we call, in this diagram, we would call steak and fish both normal goods. They're goods where as your income rises, the amount of the good purchased rises. The yellow line just connects the optimal choices, connects those dots, and you could call it an income consumption curve. But what really matters in this diagram is that as income rises, F1 rises from, or F rises from F1 to F2. As income rises to rise, F rises to F3. And ditto for S. Let's contrast the normal good with a good that we call an inferior good. And that's a good where as income rises, consumption of the good declines. So the traditional economist lore kind of story about inferior goods is that spam, this unhappy product here, is an inferior good. And so spam is being depicted on the horizontal axis, and you can see that for some levels of income, for example, as income goes from the intermediate level associated with this middle budget constraint to this high level of income associated with this budget constraint, the quantity of spam chosen goes from here to here. So income goes up, but it's supposed to be an arrow. Spam goes down. So that's what we define as an inferior good. Any good for which, when income rises, the quantity of that good consumed declines. Let's sum it up. So the good taxonomy, or the taxonomy of goods for ranges of income elasticities. Well, first of all, when income rises and the absolute quantity consumed falls, we call that an inferior good. But we can make a little bit tighter distinction for products where when income rises, the quantity consumed increases. Broadly speaking, we would call those normal goods. But we can even make a finer distinction than that. We can ask what happens to the share of expenditure on that good. Now, we can divide goods into normal goods and luxury goods. Normal goods have the following definition. When income rises, I buy more of the good, but its share of my expenditure falls. Whereas luxury goods are goods where when income rises, I buy more of the good and its share of my expenditure actually rises. Let's illustrate this, illustrate an income elasticity of demand using the Consumer Expenditure Survey. So what I want to focus on in this is like a dusty government statistics book, and I'll magnify the things you need to care about, but what you can see is expenditures on different categories of products across households of different levels of income. So what I have here circled are expenditures on housing for households with $30,000 to $39,000 in annual income versus expenditures on housing for households with $70,000 or more in annual income. Let me go to the next page. And here the numbers we care about are made a little more visible. So we're trying to calculate the income elasticity of demand for housing. Let's just do this based on a comparison of two income groups. Annual income $30,000 to $39,000, annual income $70,000 or more. So the average income in these two cells are $34.4 thousand and $124,000. What about the housing expenditure? Well, housing expenditure for the lower income group is $13,000 a year. For the higher income group, it's $26,000 per year. So first of all, is housing normal? Well, yeah, it's normal because when income's higher, the amount spent on housing is higher. But let's calculate the actual elasticity, income elasticity of demand. So how do we do that? Well, across these groups, income differs by 260%. How do I know that? Well, 124 minus 34 over 34 is 2.6. So it's 260%. And what is that? That's delta I over I. What about housing expenditure? Well, it differs 26 minus 13 over 13. And what is that? That's delta Q over Q. So it differs by 103%. What's the implied income elasticity of demand? Well, it's 1.03 over 2.6, or 0.4. So that means housing is a normal good, not a luxury. Now, how did I get that? Well, I got that this way. Delta Q over Q divided by delta I over I. And that gave me the 1.03 over 2.6 and 0.4. So housing is a normal good. It's not a luxury. Some of the answers you get in questions like this depends on how you define the product. So, a car generally might be a necessity, but if you were to look at expenditure on a Lexus or Lexuses or whatever the plural of Lexus is, it would probably look like a luxury. Low-income households spend, 0% of their income on Lexuses, whereas high-income households spend some positive percentage of their incomes on Lexuses. And so that would make Lexus look like a luxury, even if cars generally do not. Another interesting application involves Walmart and Target. And so it's possible to figure out the income elasticity of demand for goods at these stores by looking at what happens over the business cycle when incomes tend to rise and incomes tend to fall. And people who've studied this carefully find the following. The income elasticity of demand at Walmart is minus 0.5. The income elasticity of demand at Target is 0.85. So that makes Target normal and Walmart inferior. To sum it up in words, Walmart's revenues fall during good times, whereas Target's rise during good times. And the upshot of this is that, bad times can be good for some firms and vice versa. It's good to know what kind of good you are in this taxonomy. All right, what are the takeaways from this module? Well, the first thing is just that the income elasticity of demand is defined as delta Q over delta I times I over Q. There are some ranges here. Inferior goods have a negative elasticity of demand, and that means that absolute purchases decline with income. Normal goods have a positive income elasticity of demand, which means that purchases rise with income, but the share of expenditure declines. And finally, luxury goods have elasticities greater than 1. Purchases rise with income, and the share of expenditure on that good goes up.